Hello, everyone, and welcome to another Lunch&Code. Today we're going to jump in to the wonderful world of speech recognition and use an Informer RNN-T model, and I'll walk you through an open source tutorial on how to use it with a streaming API to transcribe speech in real time. Before we get started, there's a couple of things that we're going to need. We're going to use FFmpeg and sentence piece libraries. These are essential for handling audio and tokenization. These are essential for handling audio and tokenizing the input text. Now let's talk about what we're going to cover in this tutorial. The process of performing speech recognition using this model is broken down into 3 different steps. The first is building the inference pipeline. Informer RNN-T is made up of 3 components: a feature extractor, a decoder, and a token processor. Each of these play a role in recognizing and transcribing speech in real time. We're also going to format the waveform, so we'll take the incoming audio and break it down into chunks for processing. Then we need to run the pipeline, so once the data is prepped, we need to feed it through a pipeline and sort of watch it live as it outputs the transcription. So by the end of this video, we should have a clearer understanding of how to set up this Informer RNN-T for speech recognition. Okay, let's get started. Before we begin though, I think it's important to maybe talk more about the core of our model, RNN-T. RNN-T, or Recurrent Neural Network Transducer, is a model specifically designed for sequence-based tasks like speech recognition. But maybe what makes it so special for speech recognition? Here's sort of a breakdown. Unlike traditional RNNs, which struggle with real-time data, RNN-T is built to handle continuous input and output streams, which make it ideal for live speech recognition. It's designed to predict both the next token in the sequence and whether or not to output a token at each step, which means it can process speech as it comes in chunk by chunk without needing to wait for the entire audio input. As I mentioned earlier, RNN-T models have 3 main components. The encoder, which is the process. This process the input features from the audio waveform. In our case, that's when the Informer comes in, a specialized architecture that handles streaming efficiently. Then there's the prediction network. This is where the model predicts the next thing or the next token based on what it's already processed, essentially learning the flow of speech. And then the joiner, this is where the encoder's output and the prediction network's output are combined to generate the final transcription. So why are RNN-Ts useful for ASR? Traditional ASR models tend to work best when they have the entire audio available. But that doesn't really work very well for live captioning, voice assistants, and other use cases. RNN-T, on the other hand, allows us to process audio data in much smaller chunks, just enough to provide continuous transcription, but fast enough that there's almost no delay. Informer, which we'll be using, is a further optimization of this model, allowing us to process streaming audio even more efficiently by improving how it handles memory and context over time. So let's jump in to a code example and get started. We'll write some text first. So we're going to say RNN-T tutorial. And then we're going to say, we're going to build the inference pipeline Informer RNN-T. And this is going to have an extractor, decoder, and token processor. We're then going to format the waveform into chunks, and then we're going to pass data through the pipeline. And those are the 3 things we're going to do. All right, Let's move this up and let's get started. So we're going to import torch. Let's just make sure it's got PyTorch on. This is going to connect to a machine. Should have it installed. Let's find out. All right, we're good. All right, let's also use torch audio. Let's print torch dot version. Love the autocomplete. Employees mats. Wow, this is awesome. I didn't realize they added this. Wow, it even recommends what's coming next. I like it. All right, let's just run this. All right, so we got 2.4. All right. So coming back to the list of things, we are going to start with constructing some of the pipeline now. So let's do that. Really odd. Normally, yeah, there we go. Okay. So we're going to say bundle torch audio pipelines dot informer RNN-T bundle package. Then we're going to say feature. I spelled pipeline incorrectly. Feature. So spelled that incorrectly, I guess, too. I think we're good now. Feature extractor. I'm going to say bundle.get streaming feature extractor. Then we're going to say decoder, yes, tokenizer. No, got it wrong. Let's say get decoder. I'm going to say get token processor. All right, let's run this. So you can download this bundle. All right, I think we're good. All right, so next we need to sort of sample and do some chunking here. So we'll want some sort of input data with some overlap, and then we'll have sort of a main segment, write context, main segment, write context, main segment, write context. What's the best way to do this? Main context, write context. And these boxes sort of like exist like this. And it just keeps going. Let's see if this will actually show. Go this way. All right, hopefully that makes sense. So we're basically trying to get main segment, write context, main segment, write context, main segment, write context. All right, let's keep going. So now we're going to say sample rate equals bundle dot sample rate. segment length is going to be bundle.segment length plus bundle hop length. Context length is going to be bundle dot write context length plus bundle times bundle, times the bundle hop length. All right, let's print these things like it suggests. I think it's bundle dot hop length. Yeah. All right. So sample rate is 16,000. Let's maybe make this into seconds so it's easy to see. So it would be segment length frames, then segment length divided by sample rate would be the seconds. Let's do the same here, but context length. Frames. So like that. What did I do? I did something I didn't like. F strings are in. Oh. All right. So you can see here that the main segment is going to be 176. Sorry. The main segment doesn't look right. So let's make sure. Segment length is bundle segment length. Yeah, it should be times hop length. All right, that looks a little bit better. So it should be 256 frames, and then the context length is 640. So the right context is 640 frames to the diagram that I have right here, if this focuses. All right. So next what we're going to do is we're going to take the, we're actually going to go get some audio and stream it. So let's do this. Let's get some audio that I prepared earlier. Paste it in here, and then we're going to say streamer equals, to get the source, and then we say streamer dot add basic audio stream, and then we say frame per chunk is equal to the segment length. Then we say sample rate is equal to the bundle dot sample rate. Then let's print out the source. So we're going to say get source stream info. And we're going to print streamer dot get out stream info. Let's see what we get. All right. So I should get these things. So as we sort of previously mentioned, the Inform RNN-T model expects input data with overlaps. However, Streamer that we're using right here iterates the source media without overlap. So we need to sort of make a helper structure that caches part of the input from Streamer with the right context that I mentioned in this diagram, and then appends it to the next input. So we're gonna create that. We're gonna create a class to do that right now. So let's do that. So we're gonna say class context cacher, and then we're gonna say define init self, and then we're gonna do the segment length. And then we're going to do self.context. I'm going to say torch.zeros with the context length. And then say define call self chunk. Chunk is going to be a type of torch.tensor. Let's see if that auto-corrected it correctly. No, so let's do this. Let's say if chunk dot size is I think that got what we wanted. No. Let's change this slightly. We're going to say chunk equals torch. Yes, that's what we wanted. Then we're going to say chunk with context equals, and we'll concatenate the two together. Then we can say self dot context equals chunk. We'll say self.context length. Then we'll return the chunk with context. Okay. So now we have this context cacher. We can now run it with the segment length and context. So let's do that. So let's say run stream inference. I'm going to say cacher equals context cacher, so it knows the current state. Context length. Then we're going to say state hypothesis equals none. I didn't like that because I don't think this ran. Okay, perfect. Okay. So now we can start to write the inference. So I'm going to say stream iterator is equal to streamer.stream. Then we're going to display this on the screen. So let's write a quick function to do this. So I'm going to say plot feach num iter with a unit size of 25. Unit duration is segment length streamer. Segment length divided by sample rate times unit. Then we'll say number of plots is equal to num iter 1 if. Okay, got the figure and axis. Let's just do plots dot subplots num-plots. Okay, I'll do t0 equals 0. I'm just going to plot this graph. The features in feats I times units, and then we're going to say t1 equals t0 is going to be t0 plus segment length times the length of feet. Oh. Sorry. Okay. Now ax.m show we're not going to take the recommended feats. Aspect auto origin low. I think that's all we need. Okay, now ax.tick params both. And I'm going to say left is false, label left is all false. Ax.set xlim, let's say the limit is going to be t0 plus unit duration. Then we say t0 equals t1. Oh, then finally do fig.sup title, and then we'll say mel spectrogram. Okay, PLT tight layouts. All right, now we can actually write the inference, so let's just run this. Then we'll say torch.interface in inference mode. Define run inference. Number of iterations, we're going to say 1,000. And then we'll say we want global state hypothesis. We're going to set our chunks to 0 to empty. We're going to say our features are empty too, and then we're going to for I chunk in enumerate stream iterator start equals to 1. I'm going to say segments with a cacher chunk. Yes, I like that. Does not like chunk. Chunk is there. Why do you not like it? Literally, it's passed right there. like chunk. Why? Let's see if it works. I don't know why that doesn't work. So then we use the feature extractor. Let's get the segment. Then we're going to hit the hypothesis and the state through the decoder. Inference with features. Length 10. State equals state. What else do we need? Oops. Hypothesis. I'm going to say hypothesis equals hypos. Transcript equals token processor hypo 0 0 L strip equals false. It's just token processor. Wait, there's no token processor either. What? What do you mean there's no token processor? Did I run it at the start? Did not. Crap. All right. Should be good now. So let's keep going. So we can get the transcript. I'm going to print the transcript out as it is trying to pick it up. I'm going to say end equals on and flush equals true. So it'll print a new line for each one. Then we're going to say chunk start append the chunk. Do the feature stuff, feet, start append features, then break if it's at the end. Then before this return function, we're going to say plot the feats and the number of iterations, and then we're going to return Python dot display audio torch. Whoa. Literally auto completes, but it's not available. Let's go find out what. Okay, let's see if I can just use display then. It's so weird. I don't know why that worked. Torch.cats, chunks, t.numpy, the rate of the sample rate. I don't know why type is not subscribable. Okay, so it's just if the tuple is not available, that it doesn't like it. So let's do this. Let's say if chunk is non-break, and then we'll say if length of chunk is equal to 0, also break. And we'll say chunk I think that covers it. I just need some more code in there. Okay. Okay, so now I think we can just run inference on that piece of code. So before we run this, let's maybe run through inference. Run inference. Yeah, run inference. Okay, so we built this pipeline. We formatted the waveform into chunks, and now we're going to process it through the pipeline, and now we're going to run inference. So maybe just to walk you through this, so we import modules, we have this bundle that basically does all of the magic here, which is this pipeline called Informer RNN-T base, which is trained on Libra speech. We have a feature extractor that we get from that bundle. We take the decoder and a token processor too. We then, as I mentioned, sort of break up the stream for write context so we can look at it. And then we, because the reader of the stream takes the entire context of the audio, we need to sort of break it up into chunks. So we use context, so we do that. And then we use context cache to sort of take the pieces that we're using and put them in a cache. Then we created a plot diagram, which will show a spectrogram of the audio that it sees, and then we wrote the inference here. So when we run inference, we should, fingers crossed, run inference. Yeah, here we go. And this should be just continuing to predict the next sentence, the next word. All right. So this is just going to keep going through this file. And that's a spectrogram of it. All right. Sorry, I realized it was kind of small. All right. So maybe just to recap sort of the key takeaways of what we did. So RNN-T is built specifically for sequence-based tasks like online speech recognition, processing audio. As it's streamed, the Informer model makes things more efficient by optimizing how the model sort of does chunking, like we showed. And then finally we broke it down into waveform, into chunks, so that the model sort of as it goes through can continue to process and receive that transcript data that we showed as we sort of printed things out. Just to show you that one more time, if we run inference one last time on this, if I go back here and add in, one sec, and run inference one last time. I say run inference. You can see I get this text that's coming from the audio model. So you could imagine if this was real-time audio, I could then take that real-time audio and push this in, and it would transcribe as I was talking. All right, let's now move on and try and do this live with our microphone. So the goal is that we'll take the code that we just wrote and apply it to some live instance that we may need to do some tuning on, because we'll need to chunk the data and do some things. But the goal is really to take this model, this RNN-T model, and apply it to a live situation. So it'll take audio from my voice and will show the text or show text based on my voice. While that builds a font cache, let's add this. And these are basically what we took from the previous demo. As a heads up, this is a test. We didn't like that. Cacher is not defined. Okay, so I didn't need to add some more code that I didn't copy over. Let's see, cache, run inference. Okay, so I need this cache concept class here. This is how the Then I need to do this to set the parameters again. So this just says what the sample rate is. We use this. All right, this is a test. Testing 1, 2, 3. Testing 1, 2, 3. Testing 1, 2, 3. Did not print the text out. Which could be an audio issue. All right, problem number 2, I guess, is why is there no audio showing out? Let's try and debug it. The following before capturing the audio chunk. Damn, did I just reset it? So weird. Set the cacher, run inference. All right, this is a test. No. That's before it's defined. What am I doing? This is a test. Testing 1, 2, 3. Testing 1, 2, 3. Testing 1, 2, 3. Maybe it's the device number. Let's see if the feature's extracted. This is a test. Testing 1, 2, 3. Testing 1, 2, 3. Testing 1, 2, 3. Hypos. Let's run inference. This is a test. Testing 1, 2, 3. Testing 1, 2, 3. Testing 1, 2, 3. Testing 1, 2, 3. All right. Now let's just get one. Whoa, this is massive. That's something, but I need to make sure that it is. Whoa, it's too long. There we go. Damn it. Looks like it's printing. Check initialization. Check to this. Where's state? That is a good point, that the hypothesis might already be B-state. Okay, so run inference right here. Let's just take some of these out because it's kind of crazy. That run doesn't like that. This is a test. Testing 1, 2, 3. Okay, so it still gets the sizes correct. This is a test. This is a test. Testing 1, 2, 3. Okay, it still doesn't work. It says increase the chunk duration. Like maybe that's a good idea. Like chunk every 3 seconds instead. That might be better for the model. This is a test. Testing 1, 2, 3. Testing 1, 2, 3. Testing 1, 2, 3. Nope. Let's chunk every 10 seconds. Wait, chunk duration isn't even used. Why is that? Wait. Odd. Oh, I don't have audio callback, so I need to turn that on. Where is it? See if we can figure out what happened. The area scene. State, remove state initialization, print hypothesis to ensure that they're managed correctly. Yeah, so let's run inference live, and instead of doing this, just do this. All right. This is a test, testing 1, 2, 3. Testing 1, 2, 3. Okay, let's remove the features and just see if I can get the transcript. This is a test, testing 1, 2, 3, testing 1, 2, 3, testing. Nope. Something in this that's not working. Decoder outputs hypothesis. Okay. This is a test, testing 1, 2, 3, testing. Chunk duration is the one. Chunk duration, but it's not even used. I'm going to take this out. This is a test, testing 1, 2, 3, testing 1, 2, 3. Ooh. Yeah, let's check if it is silence, because then I could just be using the wrong input. It's like token decoder, no? What was the decoder again? Decoder. What's this guy? Yeah, so they're basically saying that that has to be the blank token, but what about if the audio input channel, which is SD, sound device channel 2? This is a test, testing 1, 2, 3. Okay, that's empty 2. Let's see if this works. SD query devices. Oh wait. Perfect, I know why. Oh wait, how do I select a specific audio input device to? Wonderful. So if I want to take my microphone, which is 6, I need to push it into here as device, input device 2, 6. All right, let's see if this works. All right, oh, I didn't like that. Sorry. I don't know why I'm apologizing. All right, this is the test. Testing 1, 2, 3. Testing 1, 2, 3. Testing 1, 2, 3. Let's see if this works. All right, let's stop it. There's probably just too much tokens being printed to see it. It's my guess. Let's only print if it's empty. Let's see. Let's run it. All right, this is a test. Testing 1, 2, 3. Testing 1, 2, 3. Testing 1, 2, 3. Testing 1, 2, 3. Damn, it did not work. Let's just print it and see if this works. This is a test. Testing 1, 2, 3. Testing 1, 2, 3. Okay. Let's just get the MacBook microphone, which is 8. Let's see if that works. This is a test. Testing 1, 2, 3. Testing 1, 2, 3. Let's see if the... Damn, did I take the things out? Took out the logging for the... hypos. Let's just see if this still gives the same if it's on 8. Let's see, on channel 8. Then let's run this, and it does not like it. Invalid number of channels. Okay. All right, this is a test. Testing 1, 2, 3. Let's run it. Yes, that's right. Yeah. Okay. Okay. No, it's still processing empty data. Let's see. All right, let's see if this works. Let's record some audio and see if it is an issue with the recording device. Say device equals 6. This is a test. Testing 1, 2, 3. Testing 1, 2, 3. Testing this 1. Is a test. Testing 1, 2, 3. Testing. Okay, so it does have data. It's just an issue with this. Wait, what channel did I use? 8, 6. What is in this one that just worked? Channels 1. This is a test. Testing 1, 2, 3. No. Yeah, it's weird. It works on weird, like maybe. I don't understand where it gets the chunk duration from. Because it says here while true, chunk duration, but it doesn't have chunk duration in here. Where's the one that works? All right. All right, let's do segment length and segment length. Where would that be? All right, this is a test. No, it doesn't like that. Fix the cache. Where is that cache? This is a test, testing 1, 2, 3. Run inference. This is a test, testing 1, 2, 3. No, it stopped. So adjust the input so much this better than the model for each step truncate. If the input n has more frames than this better, it will truncate it as for your frames or pad it to meet the model's requirements. Yeah, I like that. All right, this is a test. Let's see if this works. Let's fix the cacher. That didn't work either. 1, 2, 3. This is a long live stream. Will we try and run this model? All right, let's try and run the I think I'll probably just should probably just ensure the segment length is consistent. This is a test. Segment length. This is a test. Why don't I just copy what it had before, which was let's see, this is a test. Testing 1, 2, 3. Testing 1, 2, 3. Testing 1, 2, 3. Testing 1, 2, 3. It's doing something different, but it's still just got 1, 4, 4, 4, 4, 4, 4, 4, 4. it's working on something that, okay, so let's change this because I think the device equals 6. All right, let's see if that works. It seems like it's doing something different than it has been, but there is no transcript processed. Let's do this and get the transcript only. This is a test. Testing 1 2 3. Testing 1 2 3. Testing 1 2 3. Testing. Yes, that's right. Right. Yes, that's right. Yes, that's right. Yes, that's right. Yes. 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 Okay. So the hop works, but it's just empty audio. Always empty with the same decoder value. All right, what else could I try here? Try concatenating the increase your try concatenating multiple chunks of audio before passing it to model. Okay, so combine more chunks, buffer. Where is the buffer? Buffer length. Where did I put buffer? More like this. This is a test. This is a test, testing. No, what Q is doing. The Q is trying to figure that out. All right, let's see if this now works. Adding chunking to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 16, 17, 18, 19, 20. No. Okay, let's see if adding more chunks. Let's provide 20 chunks. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And. Device equals 6. Gotta remember that. 1, 2, 3, 4, 5. Oh my god, it worked. Oh my god, it actually worked. It doesn't work very well, but it does work. It picks up some very strange words here. right, let's run it one more time. 1, 2, 3, 4, 5. Yeah, that's right. It is trying to do some live processing, but it isn't that great. I wonder if I could reduce it down or up, whether it helps at all. Wow, it is strange. Okay, let's turn this off. Okay, let's move to 8. And let's combine 10 chunks and see if that works. This is a test. Testing 1, 2, 3. This is a test. Testing 1, 2, 3. Testing 1, 2, 3. Okay, so it definitely needs more chunks. So like if we increase this to 500, let's just say, let's see if that improves. So this is a test. Testing 1, 2, 3. Testing 1, 2, 3. This is a test. Okay, so it definitely needs 200 is like around. This is like tuning, I guess, but so I think it was set at 200 when it actually worked. So this is a test of it working. Yeah, and it just like picks up random words and then tries to figure it out. Yeah. Okay, now I can turn off all of this, all of the print statements that we added in here to try and fix this. Why do you not? Oh. Okay. Yeah, we're gonna print the transcript though. I think we need to add a new line to every one so that it doesn't. Let's just do this, and I think I have all the others turned off. Okay. So this is a test. Testing 1, 2, 3. Testing 1, 2, 3. Yeah. Okay. Now I need to turn off the other chunks too. Where's the print statements? Maybe it's up here. Yeah, here we go. So I printed the status on the callback and the process chunk in the. And there's probably some more optimization I could probably make with this to try and make it better. Original chunk is still showing. I don't think I need a new line with this, but I need to find the other print statements because it is going to drive me nuts. There we go. Oh, this is a test. Testing 1, 2, 3. Oh my god, it actually works. That's super cool. All right.